One very important setting that I add to probably every single rigid body sim that I run is a speed limit or an acceleration limit, or possibly both together. Now if we go back to our flipbook from that custom drag setup, you can see that there are some pieces that really fly off super fast. If you look at the top of the frame here, there are a couple really unnatural massive impulses firing those pieces off the top of the screen. Now this is really common in RBD sims. There are so many complex collisions and impulses and chaos happening here that it is very easy for those really stray, super strong impulses to happen. But thankfully, we have a good way of avoiding that. If you go back to the RBD Packed Object doc, and under Point Attributes, you can go to the Speed Limit section. You can see there are attributes you can specify per piece for the Speed Min and Speed Max, and the Spin version, Spin Min and Spin Max. And in addition to these hard speed and spin limits, there's also this Accel Max and Angular Accel Max that I believe was introduced in Houdini 16, maybe 16.5, and this will limit the change or the impulse applied to the object. So you have your hard limits and your limit on the change. And the Accel Max is typically a little bit more realistic and accurate than the hard limits are. So typically I will use the Accel Max and Angular Accel Max first, and then if I need to enforce some hard limiting in addition to that, then I might switch over to the speed limits or use them in conjunction with each other. You can absolutely use these together if you would like. I have run into some slight issues with the Accel Max before, where you can get pieces jittering on the ground plane if you have a very low value for that acceleration limit, and they give you a warning about this in the doc as well, but I just wanted to highlight that in case you run into it yourself. That sort of ground plane jitter can be caused by this value, so that's a case where you could maybe just change your Accel Max values or switch over to potentially use the hard limits instead. Now to add these limits to our scene, you can just go to our Sim Attributes Wrangle just before the simulation, and we'll just add some attributes in here. Say f at Accel Max equals, I'll just start with a value of 20, and I'll set f at Angular Accel Max, and I'll try a value of 15 for that. Now if we run the flipbook with these settings, you can see that jitter problem introduced that the docs warned about and that I mentioned I've run into as well. And it seems to me like this is really caused when that Accel Max is pretty close to the gravitational force that it's enforcing with that collision. And because in this sim we doubled the gravity force, so it is pretty close to a gravity value of 20, which is about the same as our Accel Max. So now let's raise our Accel Max so that it's not so close to that gravity value and see if that improves things. So now with a value of 100 for our Accel Max, you can see we're no longer running into that jitter problem that we were before. Now another thing that can be very helpful when setting up really any attributes on your RBD geometry is factoring in the size of the objects. So right now we've been setting this initial velocity and these Accel Max values to all of the geometry without really caring how big they are. So now if we go back to our sim attributes, we can use the bounding box size of our pieces to scale up and down any of the various attributes we're using. However, looking at the spreadsheet, you'll see that this B-box size is on our primitives, it's not currently on our points, and anything that we're using to affect our RBD sim should really be on the points. Now you could, in the sim attribute wrangle, theoretically query the bounding box size from its primitive above that wrangle, but it could be a bit easier and more straightforward if we simply promote that B-box size down to points. Now since we already have an attribute promote in our setup here, we can switch this around so that it's before our sim attribute wrangle, And we can use the same promote for both the name and the bbox size. So if you just add that bbox size to your list there, it's now available on points. And if you check the value range on that, it looks like those bbox values vary from approximately 0.1 up through 17. So in our sim attributes, instead of setting Excel max to 100, I'll use a fit function and fit the bbox size with our min and max size values set to 0.1 and 15. So these values don't have to exactly match the values that are really the maximum bbox size. Our values go up to 17, but what this will do is it'll just take anything above 15 and give it the same value, which is fine enough in our case. And then for the small pieces, maybe I'll leave the Excel max at 100, and for the big pieces, I'll lower the Excel max a bit to 50. Now, I don't really expect a massive difference in our sim just from that variance on the Excel max, so I'm going to apply a velocity multiplier as well. Maybe I'll say v at v times equals, and paste in that same fit function. And for the small pieces, I'll use a velocity multiplier of 1, and for the big pieces, use a multiplier of 0.1. Now once we flipbook this new sim, it's not super obvious, but sure enough, we are getting some different behavior on some of the bigger pieces. If you look in particular at maybe this large piece right here, you can see that's being fired off with much less initial velocity because it is significantly larger than a lot of the others. And this isn't the most beautiful sim because we've just been demoing some technical things, and in other shots you might see the difference a bit more clearly between the large and small piece behaviors, but it is a very helpful technique when you're setting these things up. Another set of attributes that can be good to vary based on the size of the object are the air resist and drag and target V attributes that work together. You can find info in the doc under the force attributes here, and this target V in conjunction with air resist and drag, which are essentially multipliers on that, can be very effective at making objects feel heavier. So whenever I want objects to feel really heavy and really pressed down to the ground in a pretty stable way, I'll often give them a very strong downward target V with a drag and air resist value, and sometimes that target V has to be much larger than you expect it to be. I would give it 0 in X and Z, but then I've used values of a couple thousand in negative Y in the past, although it doesn't always have to be very extreme. Just don't be afraid to crank that if it seems like you need to. If we go back to our flipbook and play through that, you can see there are a lot of pieces that are kind of rocking around on the ground a bit, and the target V trick is not the only way, or even necessarily the first way to fix it. I would play around with the core sim attributes first, but it's absolutely a good solution to use that target V trick to help push these things into the ground and make them feel weightier and less active when they're laying down there. Now that target V trick is really good anytime you need that per piece behavior, like if you just want a subset of your RBD pieces to push into the ground or feel more weighty. But in this particular case, everything is pretty universally overly active on the ground there. So this is a case where you could just use a normal drag force, and we could link this goal velocity of that drag force to match the gravity so that it doesn't slow down the fall of the objects. So on the gravity, if you copy the parameter for that y force, and then you paste the relative reference and the goal velocity of our drag, and you can increase the amount of drag if you want. I'll just set it to 3 on both the force and the torque, and then we can run the flipbook and see how that improves things. So now reviewing that resulting flipbook, looks like all the pieces on the ground are definitely a lot less active, and for this particular case, it looks like the drag on everything is sufficient to calm all of that ground interaction down a little bit. There's still a bit of overactivity in there that you could tweak and finesse, but we're certainly getting a whole lot closer with this simulation here.